أهلا وسهلا بالجميع. محاضرة اليوم بعنوان Double Sideband Suppressed Carrier Modulation Lecture Outline. In this lecture, we consider a second type of AM modulation called Double Sideband Suppressed Carrier. We analyze this modulation technique in the time and the frequency domains, consider the generation and demodulation techniques, study the effect of non-coherence in the phase and the frequency of the locally generated carrier at the receiver on the demodulated signal. فهاي باختصار عناوين محاضرة اليوم. A double sideband suppressed carrier signal is an amplitude modulation signal that has the form S of t equal AC M of t cosine 2 pi fct, where C of t equal AC cosine 2 pi fct is the carrier signal. M of t is the baseband message signal. Double sideband suppressed carrier modulation is simply the product of the message signal and the high frequency carrier. So this is the message M of t, this is the high frequency carrier, and the result of multiplying the signal with the carrier is what is called the double sideband suppressed carrier signal, AC M of t cosine 2 pi fct. فهاي إذن باختصار عملية الجنريشن للدبل sideband suppressed carrier modulation, and this is the formula. هون بس على سبيل المثال في عنا message signal with frequency 100 Hz and the carrier signal with frequency 1000 Hz. Upon multiplying the message signal with the carrier, we obtain a double sideband signal of this shape. هاي هي المodulated signal S of t. طبعا, as always, we impose the condition that the carrier frequency be much larger than the highest frequency component of the signal or the bandwidth of the message signal. ففي هذا المثال مثلا يعني المسج frequency 100 Hz, الكارير frequency 1000 Hz, فعنا على الأقل 10 أضعاف، يعني the carrier frequency should be at least 10 times the message frequency. الآن بنشوف الدبل sideband suppressed carrier بالفريكونسي domain. So S of t equal AC M of t cosine 2 pi fct. This is the modulated signal. We take the Fourier transform of S of t, and again we employ the modulation property of the Fourier transform. So the Fourier transform of M of t cosine 2 pi fct is simply AC over 2 M of f minus fc plus M of f plus fc. If this is the Fourier transform of the baseband signal, then the spectrum of the modulated signal is simply M of f shifted to the right by fc and shifted to the left by fc. So this is the component M of f minus fc, and this is the component M of f plus fc. طبعا we have some similarities and differences with the normal AM modulated signal. بالأول, no impulses are present in the spectrum at plus or minus fc, that is, there is no carrier transmitted as in the case of AM. Yani we observe that an impulse at fc is missing as compared to the normal AM signal. So this is what suppressed carrier means, that we do not transmit the carrier as in the case of normal amplitude modulation. The transmission bandwidth of S of t equal twice the message bandwidth. So this is a message with bandwidth W. When this message is double sideband modulated, the transmission bandwidth is Fc plus W minus Fc minus W, which is the difference between the highest frequency component and the lowest frequency component. So again, the bandwidth of the modulated signal is twice the message bandwidth. فهاي من الأشياء المشتركة أو المشابهة للنورمال AM signal من حيث الترانسميشن bandwidth. The power efficiency, which is the power in the side bands divided by the total transmitted power, is 100%. So this is a power efficient modulation scheme. زي ما شفنا في المحاضرة السابقة لما عرفنا الافشنسي للنورمال AM signal، أخذنا الباور في الأبر سايد باند والباور في اللور سايد باند وقسمناهم على التوتال ترانسميتد باور اللي كانت بتشمل الأبر سايد باند واللور سايد باند والكارير. في الحالة تبعتنا طبعا في الدبل سايد باند ما في عنا الترانسميتد كارير، وبالتالي كل ترانسميتد باور موجودة في الأبر سايد باند واللور سايد باند، وعلى هذا الأساس الباور efficiency is 100%. الشيء الآخر إنه coherent detection is required to extract M of t from S of t, as we shall demonstrate shortly, and envelope detection cannot be used for this type of modulation. So this is one aspect which distinguishes double sideband from normal AM. Normal AM can be demodulated using simple envelope detection. However, as we shall see later in this lecture, the double sideband signal can only be demodulated using what is called coherent demodulation. ناخذ مثال بسيط على الدبل sideband modulation. Consider the sinusoidal modulation case where C of t equal AC cosine 2 pi fct, M of t equal AM cosine 2 pi fmt. Plot M of t, C of t, S of t, and find their spectrum. This is the case where the message signal is simply a sinusoidal signal. So the modulated signal is the product of the message and the carrier, and equals AC cosine 2 pi fct cosine 2 pi fmt. So we have cosine, an angle, times cosine, another angle, and we have the trigonometric identity that the product of two cosines is simply the sum of the cosine of the sum and the cosine of the difference. So we have AC, AM over 2, cosine the sum, which is 2 pi fc plus fm t, plus cosine the difference, which is 2 pi fc minus fm t. So we have one component at fc plus m and another component at fc minus fm. Well, as we can see, there is no component at the carrier frequency fc. طبعا we can take the Fourier transform and the Fourier transform of the cosine. For each cosine, the Fourier transform consists of two impulses. This is the Fourier transform. We have shown only part of the spectrum for positive frequencies. المسج signal طبعا AM cosine 2 pi FMT, and the Fourier transform of this cosine is AM over 2 delta of F minus Fm plus AC over 2 delta of F plus Fm. So we shift these two deltas to the right, and we shift these two deltas to the left. So in the next figure, we show all the plots required in this example. ففي المثال السابق, this is the message signal, AM cosine 2 pi 100t. This is the message signal. The message signal is shown here in the time domain. It's a sinusoidal signal which varies between -1 and 1. Okay? In the frequency domain, the Fourier transform of the cosine consists of two impulses, one impulse at 100 Hertz and another impulse at -100 Hertz. As for the carrier 2 pi 1000t, this is the carrier in the time domain. In the frequency domain, the carrier consists of two impulses, one impulse at 1000 Hertz, another impulse at -1000 Hertz. Now, S of t, which is the product of the message and the carrier, plotted here in red. In the frequency domain, we have a component at 1100 Hertz and another component at 900 Hertz. The component at 1100 Hertz, this is the upper sideband. The component at 900 Hertz is the lower sideband. The spectrum consists of an upper sideband, a lower sideband, and there is no carrier. فهذا إذن بورجينا السبكترم للمودulated signal. Generation of double sideband suppressed carrier signal, the product modulator. The product modulator simply multiplies the message signal M of t with the carrier C of t. This technique is usually applicable when low power levels are possible and over a limited carrier frequency range. الطريقة اللي مشهورة أكثر ومعروفة أكثر وإلى استخدامات أكثر هي الرينج modulator. Consider the scheme shown in the figure. We have a transformer. M of t is applied to this side of the transformer, and we have this side of the transformer. We have another transformer and another transformer and a bandpass filter. The carrier is applied between the center of this transformer and this transformer. Also, we have four diodes, D1, D4, D2, and D3. These diodes are connected in a form which is called the ring. So, we assume that the carrier frequency C of t is much larger in amplitude than the message signal. So this is the carrier, so this is the message signal. طبعا والسبب that the reason for imposing this restriction is that we need the carrier to control the mechanism of opening and closing these switches, these diodes. So during the positive half cycle of C of t, SC of t is positive, and D1 and D2 are on, while D3 and D4 are off. In this case, Y of t equal M of t. This is the carrier. During the positive half cycle, the potential at this point is higher than the potential at this point, which means that this diode will be on because the potential here is larger than the potential here. So D1 will be on, D2 is also on, while D3 and D4 are reverse biased. These two diodes are reverse biased because the potential at this point is smaller than the potential at this point. So this diode is off, this diode is off, this diode is on, this diode is on. Therefore, we have the message, and this message is transformed via this transformer all the way to the output. So this is the model of the circuit during the positive half cycle when D1 and D2 are on. The message, which appears at the primary terms of the transformer, are induced here and also will be induced at the output. So during this positive half cycle, the message M of t at the input will also be the output of this switching modulator. During the negative half cycle of C of t is less than 0, D3 and D4 are on, while D1 and D2 are off. Hence, Y of t equal minus Y of t. Now, during the negative half cycle, the polarity is reversed. So this point now becomes negative as compared to this point. So this point has a higher potential than this point, which means that now this diode is on and also this diode is on. D1 and D2 are now open circuit. They are reverse biased and our circuit looks like this. So what we see at Y of t, not M of t, but rather minus M of t because of the change in the polarity of the transformers. So during the positive half cycle, the output Y of t equal M of t. During the negative half cycle, the output Y of t is minus M of t. So M of t is multiplied by plus 1 during the positive half cycle and by minus 1 during the negative half cycle. So this is the switching mechanism where the output, this output, is either multiplied by plus 1 during the positive half cycle of the carrier and multiplied by minus 1 during the negative half cycle of the carrier. Okay? هلا بدنا نطلع على الماثماتيكال موديل وبعدين نحكي عن الاوبريشن للباند باس فلتر. So M of t is multiplied by plus 1 during the positive half cycle of C of t, and M of t is multiplied by minus 1 during the negative half cycle. Mathematically, Y of t behaves as if M of t is multiplied by the switching function Gp of t, where Gp of t is the square periodic function with period Tc equal 1 over Fc. So this is the positive half cycle, and during this time we multiply the message by plus 1. During the negative half cycle, we multiply the message by minus 1. The frequency of this square function is the same as the frequency of the carrier. So this is a representation of the mechanism where D1, D2, D3, and D4 behave over one complete cycle of the carrier. So y of t equal m of t, gp of t, this switching function, and we can expand this function in a Fourier series, and the Fourier series of this square function is وجدناها طبعا سابقا. We have found this representation in a previous lecture. M of t equal 4 over pi cosine 2 pi fct minus 4 over 3 pi cosine 3 times 2 pi fct plus 4 over 5 pi cosine 5 times 2 pi fct plus higher order harmonics. Now we multiply m of t with each one of these terms. So we have m of t times 4 over pi cosine 2 pi fct minus m of t times 4 over 3 pi cosine 3 times 2 pi fct plus m of t 4 over 5 pi cosine 5 times 2 pi fct plus higher order terms. طبعا بدنا نيجي الآن ونشوف ايش الدور اللي بيعمله الفلتر. Y of t is applied to a band pass filter, and the role of the band pass filter is to admit only a double sideband signal around the carrier frequency Fc and suppress all other high frequency terms. So this is what the function of the filter is. M of t times cosine 2 pi fct, this is a double sideband signal around the carrier frequency Fc. يعني بتاخد الشكل message times the carrier. These terms are high frequency terms and they can be suppressed by the band pass filter. So this term will be rejected by the filter. This term will also be rejected by the filter, and the only term admitted by the filter is this required signal m of t 4 over pi cosine 2 pi fct. When y of t is passed through the band pass filter with carrier frequency Fc and bandwidth equal to W, the only component that appears at the output is the desired double sideband suppressed carrier signal, which is our signal 4 over pi m of t cosine 2 pi fct. It's in the standard form of a double sideband suppressed carrier signal, which is, we can assume that this is the amplitude of the carrier, this is the message, and this is the cosine term. Demodulation of double sideband suppressed carrier signal. A double sideband suppressed carrier signal is demodulated using what is known as a coherent demodulator. This means that the modulated signal S of t is multiplied by a locally generated signal at the receiver, which has the same frequency and phase as that of the carrier C of t at the transmitting side. This is a representation of the structure of the receiver. We have an incoming double sideband signal AC m of t cosine 2 pi fct. In order to demodulate this signal properly, we have to multiply it by a locally generated signal AC prime cosine 2 pi fct, which has the same frequency and phase as those used at the transmitting side. So this here is cosine 2 pi fct. This also has to be 2 pi fct. We multiply this signal by this carrier and then pass the result through a low pass filter. فهلا بنورجي الماث تبع demodulation. We start first with what is called perfect coherent demodulation. And with perfect coherent demodulation, we mean that the carrier at the transmitting side equal AC cosine 2 pi FCT. The locally generated signal at the receiver side is AC prime. It's just a constant, cosine 2 pi FCT. Both of these two signals have the same frequency and phase. Now mixing the received signal with the version of the carrier at the receiver side, we have V of t equal S of t times C prime of t, S of t times AC prime, cosine 2 pi FCT equal AC prime, M of t, and we have cosine times cosine square 2 pi FCT. And we can again make use of the trigonometric identity. Cosine square theta equal 1 plus cosine 2 theta divided by 2. So we have AC prime over 2 M of t, and cosine square equal 1 plus cosine twice the angle 2 times 2 pi FCT, and this here we divide by 2. We expand this term. We have AC prime over 2 M of t plus AC prime over 2 M of t cosine 2 times 2 pi FCT. So upon mixing these two signals, we have a component of V of t which is proportional to the message signal plus another high frequency signal. This high frequency signal is nothing but another double sideband modulated signal around twice the carrier frequency FC. الآن, since we're doing demodulation, we have to get rid of the high frequency term and admit only our desired signal. So we have a low pass filter with bandwidth W, and this low pass filter will admit the message signal M of t and will reject the high frequency term. The first term on the right hand side is proportional to M of t, this term, while the second term is a double sideband signal modulated on a carrier with frequency 2 FC. The high frequency component can be eliminated using a low pass filter with bandwidth equal W. The result, of course, is Y of t. This output here is AC prime over 2 times M of t. Therefore, M of t has been recovered from S of t without distortion, i.e. the whole demodulation process is a distortionless one. طبعا يعني شرط الديستورشنلess هو وجود كارير عند الريسيفر سايد اللي له نفس الفريكونسي والفيز زي الكارير اللي استعملناه عند الترانسميتر. طبعا ما في مجال ان نقدر نسترجع المسج سيجنال من خلال envelope detection مثل ما عملنا بالنورمال amplitude modulation، وانما فقط يتم استخراج السيجنال من خلال الكوهيرنت demodulation. فهي الحالة الأولى اللي بنقدر نسترجع فيها السيجنال بدون ديستورشن من خلال perfect coherent demodulation. الدبل سايد باند suppressed carrier signal يعني حساسة من حيث الفيز والفريكونسي للكارير اللي بنستعمله عند الريسيفر سايد. فرح ندرس حالتين اللي نغير فيهم من الفيز، مرة بنغير الفيز ومرة بنغير الفريكونسي للسيجنال اللي بنستعملها عند الريسيفنج سايد، وبنشوف تأثيرها على الديمودوليتد signal. So the effect of carrier non-coherence on demodulated signal, constant phase shift. This is the first case where the locally generated signal differs from the transmitted carrier by a constant phase phi. So this is cosine 2 pi fct, this is cosine 2 pi fct plus a constant phase shift. So the carrier at the transmitting side, C of t equal AC cosine 2 pi fct. Our locally generated carrier is AC prime cosine 2 pi fct plus phi. Now we use the same demodulator as the one we used before, so we mix the incoming signal with the locally generated carrier. V of t equal AC m of t cosine 2 pi fct times AC prime cosine 2 pi fct plus phi. So we have AC prime m of t. Again, we have cosine 2 pi fct and cosine 2 pi fct plus phi. So we have cosine times cosine, and that is again cosine, the sum plus cosine, the difference of the two angles. So m of t, we have the sum 4 pi fct plus phi, and the difference is just cosine phi. We expand the product, so we have AC prime over 2 m of t cosine 4 pi fct plus phi plus AC prime m of t cosine phi. We recognize that this is a high frequency term, and this term is a low frequency component. So in essence, this component will be rejected by the low pass filter, and this component will be admitted. The low pass filter suppresses the first high frequency term and admits only the second low frequency term. The output is y of t equal AC prime m of t cosine phi. What is the effect of the phase difference phi on the demodulated signal? If phi is zero, then we have perfect coherence, and y of t equal AC prime over 2 m of t. If phi is an angle between 0 and pi over 2, less than pi over 2, then the cosine is a positive quantity which is less than 1. So in this case, the effect of cosine phi is merely an attenuation of the signal. So the value of the signal at the output will be diminished by the factor cosine phi. So y of t suffers from attenuation due to phi. However, if phi is exactly pi over 2, if phi equal pi over 2, this means that cosine phi equal to 0, and in this case y of t equal to 0. That is, the receiver loses the signal, and this highlights the importance of coherence between the transmitter and the receiver. If we lose coherence, this means that we can also lose the signal, that this structure will no longer be able to demodulate the signal. If phi is pi over 2, then nothing will be observed at the receiver output. The disappearance of a message component at the demodulator output is called quadrature null effect. This highlights the importance of maintaining synchronism between the transmitting and receiving carrier signals. C prime of t and C of t. C of t is the carrier used at the transmitting side. C prime of t is the locally generated copy of the carrier. خلينا نوضح تأثير الفيز في حالة sinusoidal modulation. So the effect of carrier non-coherence on the modulated signal for the case of constant phase shift. Example, let m1 of t equal cosine 2 pi 1000 t, m2 of t equal cosine 2 pi 2000 t, and the total signal, the message signal, is the sum of these two harmonic terms, m1 of t plus m2 of t. We use a carrier with frequency 10 kilohertz, C of t equal cosine 2 pi 10,000 t, and let phi equal 50 degrees. From the analysis above, we have y of t equal AC prime over 2 m of t cosine phi. The next figure shows the input message, the carrier, the modulated and demodulated signals in the time and the frequency domain. This m of t is this m of t, the sum of two harmonic terms. This is the locally generated carrier with phi equal 50 degrees and the frequency equal 10 kilohertz. M1 of t cosine 2 pi 1000 t, M2 of t equal cosine 2 pi 2000 t, and m of t equal m1 plus m2. So this figure here is our message signal m1 plus m2. This is the message signal in the time domain. In the frequency domain, we have for each cosine there are two impulses. So we have one impulse at 1000 hertz, at minus 1000 hertz, 2000 hertz, and minus 2000 hertz. So this is the spectrum of our message signal. The message consists of two harmonic components. The carrier C of t, shown here in black, is a cosine function with frequency 10 kilohertz and 0 phase shift. So this is the carrier frequency, the curve in black. C prime of t is this carrier with this delayed phase shift of 50 degrees. So it is this other curve. In the frequency domain, this constant phase shift has no effect, and so the Fourier transform of both carrier signals are the same. We have one impulse and another impulse, both of them at 10 kilohertz. The modulated signal S of t is of course the product of the message signal and this black carrier cosine 2 pi 10,000 t. In the frequency domain, as we observed, the spectrum of the modulated signal can be obtained by shifting the spectrum of the message signal to the right by 10 kilohertz and to the left by 10 kilohertz. So we have this upper side band signal. So we have an upper side band with 11,000 hertz, and 12,000 hertz, and the lower sideband with frequencies of 8,000 and 9,000 hertz. So this is our upper sideband, this is our lower sideband, and there is no carrier at 10 kilohertz. So this is the spectrum of the modulated signal. Now the effect of demodulation, when we multiply by the locally generated carrier with the same frequency but with a phase shift of 50 degrees, we observe that we can recover the message signal. However, the message suffers from some sort of attenuation. As we can observe, the shape of the signal is maintained. However, the amplitude has been reduced. In the frequency domain, again, we observe the same thing, and we can recover the signal. So in this case, as long as the phase angle is not 90 degrees, we can recover the signal without distortion. فهذا إذن أهمية الفيز شيفت، إنه طالما الفيز شيفت ما كان 90 درجة بإمكاننا نسترجع السيجنال بدون ديستورشن. إنما إذا كان الفيز شيفت يساوي 90 درجة معناته مش راح يكون في إمكاننا إن نسترجع السيجنال، أصلا راح يكون الأوتبوت يساوي صفر. الحالة الثانية اللي بدنا ندرسها اللي هي الكونستانت فريكونسي ديفرنس، الحالة الثانية من non-coherence. So the constant frequency difference between C of t and C prime of t. Again, we assume that the carrier frequency is Fc. However, in this case, the locally generated frequency at the receiver differs from that at the transmitter by a frequency delta F. So this is the signal which we use at the demodulator. It's an AC prime cosine 2 pi Fc plus delta Ft. So C of t equal AC cosine 2 pi Fct. This is the carrier at the transmitting side. C prime of t equal AC prime cosine 2 pi Fc plus delta Ft. This is the locally generated carrier, and as we observed, it differs from that at the transmitting side by an amount delta F. Again, we use the same procedure. We multiply this signal with this signal, and the result is V of t equal AC M of t cosine 2 pi Fct times AC prime cosine 2 pi Fct plus delta Ft. Again, we have a cosine times cosine and cosine times cosine. We have cosine the sum plus cosine the difference. And cosine the sum, we have AC prime over 2m of t, cosine 4 pi Fct plus 2 pi delta Ft. This is a high frequency component which will be rejected by the low pass filter. AC prime over 2m of t cosine 2 pi Fct is a low pass component, and as such will be admitted by the low pass filter. So after low pass filtering, the output y of t is AC prime over 2m of t cosine 2 pi delta Ft. الآن, is this a distortionless transmission? The answer is no. Y of t does not equal to a constant times the message m of t. Rather, y of t equals some function of time times the message m of t. Therefore, this is not a distortionless transmission, which means that failing to obtain a frequency at the receiver side which equals to that used at the transmitting side means that we will have distortion of the output signal. As you can see, y of t does not equal to a constant times m of t, but rather m of t is multiplied by a time function. Hence, the system is not distortionless. In addition, y of t, this y of t, appears as a double sideband modulated signal with a carrier frequency delta f. So, y of t equal m of t cosine 2 pi delta ft. So, delta f appears as the new carrier frequency for m of t. فهي طبعا this is a type of distortion resulting from failing to maintain synchronism between the transmitting and receiving carrier frequencies. بنوضح هاي الظاهرة من خلال مثال. Let m of t equal cosine 2 pi 1000 t, c of t equal cosine 2 pi 10,000 t, and let delta f equal 500 hertz. From the analysis above, y of t equal AC prime over 2, m of t cosine 2 pi delta ft. M of t is this test signal cosine 2 pi 1000 t times cosine 2 pi delta ft, cosine times cosine, so we have AC prime over 4 cosine, the sum which is 1500 plus cosine 2 pi 500 t. So the output y of t consists of two frequency components, one at 1500 hertz and another at 500 hertz. The original signal is a signal with a single frequency of 1000 hertz. This is our message signal. It's a signal with 100 hertz. The output of the demodulator consists of two frequency components, and 1000 is not one of them, while the output consists of a signal with two frequencies at f1 equal 1500 and f2 equal 500 hertz. So we observe this type of distortion. So the output y of t is no longer proportional to the input m of t. هاي الرسمات بتورجينا الميكانيزم للمثال السابق كيف صار عندنا الديستورشن. So the message signal is the test signal 2 pi AC cosine 2 pi 1000 t, the carrier cosine 2 pi 10,000 t, C prime is cosine 2 pi 10,500 t. So 500 is the difference in the frequency between the carrier used at the transmitter and the carrier used at the receiver. So delta F equal 500. Here M of t, our test signal, consists of two components at 1000 hertz minus 1000 hertz. So these are the two impulses with a frequency of 1000 hertz. Now the black curve is the sinusoidal signal, the carrier cosine 2 pi 10,000 t. The black one cosine 2 pi 10,000 t. The locally generated signal cosine 2 pi 10,500 t is the other yellow curve, again plotted on the same figure as we see they drift from each other as time progresses. In the frequency domain, we have one impulse at 10,000, another impulse at 10,500. So this is the Fourier transform of the carrier at the receiving side. The black one is the Fourier transform of the signal at the transmitting side. Of course, this is S of t obtained by multiplying the message signal M of t with this carrier C of t equal cosine 2 pi 10,000 t. Again, we have an upper side band at 11,000 Hertz and a lower side band at 9,000 Hertz. As for the demodulated signal, we have this output in the time domain, which is quite different from the message signal M of t. This signal here is the sum of two sinusoidal terms at 500 and 1500 Hertz. In the frequency domain, we have one component at 500 and another component at 1500 Hertz. فهذا المثال طبعا بورجينا انه عملية السينكرونايزيشن بين الترانسميتر وما بين الريسيفر شيء مهم جدا بالنسبة للدبل سايد باند suppressed carrier modulation. A double sideband suppressed carrier signal cannot be demodulated using coherent detection as in the case of normal amplitude modulation. However, the demodulation process is more complex in the case of double sideband. It requires maintaining synchronism between the carrier used at the transmitting side and the locally generated carrier at the receiving side. Both of them have to have the same phase and the same frequency. فهاي نهاية المحاضرة. إلى اللقاء.